In this section, we continue concepts on time value of money, TVM. The slide in front of you right now explains, or displays rather, the difference between an ordinary annuity and an annuity due. The number of payments for the two annuities remains the same. The critical difference, however, is that the payment shifts up by one time period when the annuity is due. An example of an annuity due is rent. Most annuities are ordinary annuities where the payment is at the end of the time period. So it's like you work for a month and then your payment comes at the end of the month. However, for something like rent, you pay the rent up front and then you live for the rest of the month there. This has important implications for the calculation of present value and future value of these two streams. Let's see what we have there on the next slide here. So for an ordinary annuity here of $100 at 10% for 3 years, you can see that the $100 is deposited at the end of the first time period, at the end of the second time period, at the end of the third. So simple compounding would result in 100, 110, and 121 terminal values. How do you get 121? That's 100 times 1.1, so that's 110. However, the compounding effect takes place, and then 10% of 110 is 11 bucks, so 11 plus 110 becomes 121, and so the total is 331. With an annuity due, it would be different. These payments would be at the beginning, and so basically there's one extra interest period which the which adds to the terminal value of an annuity due stream. Here's an illustration of the present value of an ordinary annuity. 100, 100, and 100. How do we get 90.9, 82, and 75? You divide it by 1.1 to the power 1, 1.1 to the power 2, and 1.1 to the power 3. And you get 75.13. You add them up, and that's the present value of the ordinary annuity. The finance calculator solution of this is easy to obtain. You enter these three values. Let's actually do that. So it's 3 years, 3. Remember, you enter the value first and then the associated function key. 10 years, payment is 100. Future value is 0. Compute. Present value minus 248.69. So you have payments but no lump sum future value, so we entered 0 for the future value. What would the present value and future value be if it was an annuity due? As I mentioned, you have the $100 deposits at the beginning of the time period. There are two ways to look at this. One is, if you've already calculated, like we did in the previous slides, we already have the present value and future values of the ordinary annuities, not the annuity dues. Then you can multiply it by the 1 plus I factor, and in both cases you're going to get a higher terminal value, as I mentioned earlier, because the payment is existing for one extra time period. So in this case is 1 plus 0.1, and you multiply that by 248, you get 273, 364. We can actually replicate this, and that's why I have the calculator here open, is using the calculator. So in case you don't want to do this, your calculator has a function built into it for this. Switch from end to begin mode. Excuse me. Switch from end to begin mode, and then enter the same variables to find the present value of the annuities. We actually have these numbers, and this 248 I'll show you will actually become 243 by switching some other keys here. Let's clear the screen, second, begin. So see, there's BGN, that's the begin mode. So you hit the payment button, but actually in the second mode. And now it's prompting you to hit set. Now you can't hit set directly, as you can see. So you have to invoke the second button here, second, set. And now you're in begin mode. If you clear the screen, you'll actually see. So this is actually a very interesting and useful feature built in the calculator, but it also can be very, I mean, not dangerous, but if you forget to revert back to the benign state, if I could say that, then all your calculations will basically be off by 1 plus I. So you want to do that. I'll show that to you in a second. So now that it's in the begin mode, let's hit compute present value, and you get 273.55. So I didn't change any of the values. They were already there in the memory of the calculator. So you have the same numbers there. Instead I did second PV, and you get 273. Now if you make PV equals 0 for this stream of payments, which in this particular case are annuity dues, and you compute the future value, you'll see it'll be higher. Compute future value, that's 364. So it seems like just a bunch of numbers I'm throwing at you, but frankly there is a little bit of method to this madness. It's 364.10. Let's compare this here. Let's go back. You see this? If the begin mode wasn't there, it was 331. You multiply it by 1.1, you get 364, which is also we are able to replicate with the calculator. So actually it all hangs together. In fact, this is a nice opportunity I'll take to undo the begin mode, and I'll just hit compute FV, and we should get 331. So let's do this. Second, begin, second, set, and you see it goes away. Clear the screen. Now the values are still there, stored in the associated function keys there. Let's hit compute FV, and there you go, 331. So just by changing the begin to end mode, we are switching between 364 and 331. It's actually simple stuff. It's but probably not intuitive, and the only way, you know, it'll become second habit if you do a little bit of practice. So I rely on you for doing that. I already showed you this here. You can also use Excel to calculate annuities due. In fact, everything that we've done here on the calculator, you can invoke an Excel function. And I'll just illustrate this here using this. You can try it out. This present value here is got 1, 2, 3, 4, 5 arguments actually. The fourth term's 0 tells the function that there are no other cash flows, just these. And 1 is the interesting one in this case. It says whether it's an annuity due or ordinary annuity. The default state is 0. A similar function is for future value. You can check it out. This is about uneven cash flow streams. I'll get to that in a second. Some of you must have thought that, well, Hank, you know, he skipped through some slides here. So I was here, and then you notice this super TVM question. I actually have an associated screen capture video, which is actually posted, which goes into that. But since we are here, I'll just quickly give you a recap of this. This sort of a interesting, funny question, you know, is a fellow finance professor asked me this many years back. Suppose you can take a penny and double your penny every day for 30 days. What will you be worth? So, you know, penny becomes 2. So here it is 2, 4, 8, 16, 32, 64. And after about 10 or 12 days, it's 8,192 cents. That's basically $81. So when I do this live in my classrooms, people usually come to some numbers like $3,000 to $10,000. But as you see, the terminal value of this arrangement, if I may say, is about $10 million. How do we get that? Just clear the screen there. So your present value is $0.01. And we put a negative because you're depositing it. So basically you found a banker who's willing to double your penny every day. Now double a penny is different from adding a penny, okay? So there's like little things buried in there. What do you think is the interest rate here? If something doubles, that means 2 minus 1 divided by 1. So that's equal to 1, which is 100%. So basically, you found a banker who's willing to give you 100% return on investment on a daily basis. So there is the magic recipe for getting to the 10 million. So it's sort of a trick actually. And number of time periods is 30. See, we don't care whether it's 30 years, 30 days, because we have defaulted this XPY. You can see it. Actually, I can show it to you here. Second XPY. Okay, let me clear this. Actually, the second PY. See, second PY is 1. So that means payments per year is 1. The default state in your calculator, if you bought it new, is 12, and you want to change that to 1. And so then it becomes unit neutral, whether it's month, days, it's just. So it becomes more powerful basically if you set it this way. Anyway, let's get back to our penny question. So n equals 30 we entered. Um, just to be sure, just enter it again. N equals 30. IYPV, PMT is 0. We are not adding any additional pennies. We have given the penny to the banker, and the banker is doubling it every day. So the payment is 0. Now here, compute future value, and there you see 10,737,000 and extra digits there. So that's the super TVM problem that I mentioned. Next topic here is what is the present value of an uneven cash flow stream. Now this is a new topic here, and this can get pretty dicey and tedious. Nothing complicated again, but tedious. The problem here is you cannot invoke the PMT button, this PMT button, because this requires equal amounts at equal intervals of time. Now you just notice the amount is not equal here. So what if you started a restaurant, let's say, and after the first year generated $100 or 100,000, and then 300, and then you had to fourth year was not that good, and you had to undertake some capital adjustments and new equipment and so on and so forth, capital additions, so you had a profit, you had a loss of $50 actually here. So how would you calculate the present value of this uneven cash flow stream? Well, the basic setup is the same actually. You divide 100 by 1.1 to the power 1, and you should get 90.91. Divide 300 by 1.1 squared, and you'll get that. And minus 50 divided by 1.1 to the power 4, 1, 2, 3, 4. Actually, let's just do that here. Not that we need to, in a way. So you got 50 here with a negative sign. Divide. Always safe to use this parentheses here. 1.1 to the power 4. And there you go, minus 34.25. Interesting here. Change that. Minus 34.25. And you can make some adjustments here. Um, so you have that, and you can do it like that. But what if these are 30 streams and all the numbers are all over the map? So this is what you do. Your calculator has a built-in cash flow register. Here's the cash flow register here. And let's just cycle through this. You got CF0, C1, F, and so on and so forth. CF0 is always the first cash flow, which is typically an investment. And so it would be a negative number. But in this case, we don't have an initial amount, so we enter 0. So you enter 0 here. Remember to hit the enter button, otherwise it does not register it. Then C01 is 100. Once again you hit enter, and then the default F01 is 1. F is basically the frequency of a cash flow, and if you have more than one cash flow with the same value to save yourself labor, you can actually enter that, which we'll do in the second case. But here is 1. C02 is 300. Enter. And this time the frequency is 2 because the frequency of a payment amount of 300 is 2. And now this C03 actually corresponds with CF4 because here we had the second 300 as a separate cash flow. So it's 50 with a negative sign. Hit enter. 1. Now notice there's something that will happen. C04 is 0. Please don't hit the enter button because that would register as 0 cash flow, which is a valid number. And you'll notice that F04, if you don't hit enter, the F04 is 0. So the calculator is now basically telling itself that there are 0 cash flows of $0 at that time. Always cross check what we have entered. So CF00 okay, 100, 1, 300 should be 2, and 50 should be 1. Alright, so we're good to go here. Hit the clear button. Now hit the NPV button. That's net present value. Net present value is a derivative of present value, where it's the sum of the initial investment plus the present value of the future cash flows. And in this case, our initial investment is $0. And so we can use net present value. So we are using this. So it's sort of a backdoor to calculating the present value of uneven cash flows. So let's see what this function has. You got I, which is probably the interest rate, and NPV with the CPT means compute. So basically there are two elements for this function, I and NPV. So you need to know the interest rate because that's the discount rate. So we enter 10%. You don't have to convert to decimals. Hit enter. And NPV, hit the compute button. And that's 530.09, which is what we have here. So in this case, NPV is equal to present value because, as I said, your initial investment is 0. So this is a very nice, powerful feature of this calculator where you can calculate the present value of uneven cash flows. Now, as I typically do, I'll show you, how you can do this in Excel also. And so here's the basic function NPV. The interest rate you enter here, and notice that this will actually be a decimal. So in Excel, this will actually be 0.1. And this is the array that you put in, B2 to E2. So what's B2 to E2? So this is where your cash flows are. So you can imagine you can put like literally, 50 or 100 cash flows in there. And these are your time intervals. The next topic is, by the way, all of finance, is basically doing something like this. Like when Facebook went IPO, what were people trying to do? They were trying to estimate what the future cash flows of the company would be and for how long, and what the interest rate would be in that over that horizon. So think about how many variables I just introduced. One is you have to know the value of these cash flows. 2 is the duration of these cash flows. And 3 is what the interest rate in the future is going to be. And once you have all that, then you estimate its present value, because present value is what is happening right now. So if thinking of the Netscape IPO, if Facebook wants to go IPO, the investment bankers want to ascertain what should the price of the initial offering be, because that is what is relevant. And if you remember, in 2012 the company went IPO and the initial offering price was $38, and then within 3-4 months it got cut down to $19, which basically meant the market cap went from $80 billion to $40 billion. But then it bounced back and it's trading above $40. So it's all about the present value of the expected cash flows. And I could take that opportunity to sort of highlight something that sometimes students talk to me about is I think the critical difference between accounting and finance is accounting is counting what has happened in the past, and finance is discounting what will happen in the future. So this is a nice little illustration of that. These cash flows have not happened. They are going to happen, or we expect rather that they're going to happen. And so therein lies the big difference between the two related fields. As far as I think, I mean, the difference between the two is almost like the difference between botany and zoology. They're both in biology. So accounting is a whole separate subfield. I mean, you have a doctorate in marketing, a doctorate in finance, a doctorate in accounting, doctorate in management. So they're pretty diverse fields, but they are all related, of course. Anyway, the next topic is basically this topic is about calculating the effective annual rate. And it's important, for more than one reason. Of course, it's fundamental to this chapter and concept of in time value of money. But I actually think that students and people should really know what the effective annual rate is, because the market actually calls it APY, that's annual percentage yield, and that's the term that is used. And this is actually what you, as a borrower, are actually paying. So I encourage you to look at your credit cards, and you will find the APR stated there. The APY is often not stated. So it's only stated, when you're buying a CD, so that it makes the CD look better, that the effective yield is higher than the stated return on that. And so I'll show you a couple of ways of how to actually calculate the APY. So that is the topic for the next 10 slides or so. So the nominal rate is stated in contracts. It's actually not used in calculations. And the periods must be given. So 8% quarterly, 8% um, compounded daily interest. And so typically it's annual, but then it can be, the periods must be given also, whether it's compounded quarterly or annually, because that will make a difference in the terminal effective rate. The periodic rate is actually simple. It's basically what your nominal rate is divided by the number of compounding periods. So for quarterly it's 4, for monthly it's 12, and for daily it's 360 or 365 it's used. So 8% quarterly, so interest per period is 2%. For daily, it looks a little bit more, messy, but that's what you have here. The adjustment that is done when you have multi-period compounding, different compounding periods, is you take the nominal interest rate and you divide it by the number of compounding periods, and n, which is your total number of years, you multiply that by the number of compounding periods. So let's say in this case we have $100 at 12% nominal with semi-annual compounding. So semi-annual compounding, so m equals 2 here. And so in 5 years, basically you've got 10 semi-annual slots, right? And but you're earning 12% a year, but the interest rate, the nominal interest rate that's being applied per 6 months is actually 12 divided by 2, which is 6%. And what happens is the implication of multi-period compounding is that the terminal value is higher. So if you are a lender, so if you're depositing money in a bank, it is to your advantage that you have daily compounding as opposed to monthly, and you'll be worse off if it's annual compounding. And that's an illustration right here. You can see with annual compounding, the terminal value of this is $176. With semi-annual compounding, it's $179, because there's interest on interest. As Einstein said, the greatest force on earth is the power of compounding, as reportedly said at least. So here I can actually show you this. So this is, and you should verify this. So you can see you have the same $100 and same 5 years, same 12%. The only difference is here, annual, semi-annual, quarterly, monthly, and daily. And for daily, it's 12%. So since we're using the core formula here, divide by 365, and number of compounding periods is 5 times 365, that's 182. So if you're looking at like $100,000 investment, the difference is from $176,000 to $182,000. And that is actually, how actually value is added without actually taking on any additional risk. And financial institutions know that. Now, if you're a borrower, it'll hurt you because you'll end up paying more. And you should see, what your credit card statements say. So I'm continuing on with this topic. I'll show, this actually, in case you're wondering, I'll show you how to do this in a very quick and efficient way using your financial calculator. So basically, the effective annual rate is the rate which causes the present value to grow to the same future value as under multi-period compounding. So with the 12% semi-annual, the future value is 1.12. You take the 1 out, so that's 12.36%. So the effective rate is 12.36%. So this is an interesting way to put it right here, is the 12.36% indicates, because if you invest a dollar at 12% semi-annual compounding, it would grow to the same value as the dollar invested for 1 year at 12.36. So if that dollar is invested for 12% annual, your terminal value would be $1.12. But with semi-annual, it will actually be 12.36. So that's the effective rate, the implication of multi-period on the effective rate. So how do we find effective annual rate using our friendly calculator? Basic formulation is this. This looks like a new formula, but if you take the 1 over on this side, is 1 plus effective annual rate, which is basically the interest rate. And this is the adjustment with the multiple periods. And this is, since for 1, you don't see the time here. Otherwise, it's m to the power n and m multiplied by n here. What is m? Is the number of compounding periods. So what is the effective annual rate of 12% compounded monthly? So we can do this. We've done this in the previous slides, and it's 12.67. Let me show you how to do this here. Hit second, iconv. Now there's something new here. Iconv is behind the button 2. And let's just go up and down here, see what's there. So you got norm, which is nominal, EFF, which is effective, and CY is the compounding periods per year. Actually, I've done that for 12. But let's say nominal is 12, and so I'll use a different example here. And let's do this one here, because already we have 12 there. What is the effective annual rate of 12% compounded daily? So now you got to enter the number of periods, which is 365. Enter. And effective. Hit the compute button and see that's 12.75. So you see, from 12% you can go to 12.75 just by changing the compounding periods. And so this is a nice function that can be used. You can actually, once again, pull your credit card statement and see what the effective rate you're paying. And these are some numbers, same information there, you can verify it. Can the effective rate ever be equal to the nominal rate? Yes, only if the compounding is annual, i.e. if m equals 1. If m is greater than 1, the effective rate will always be greater than the nominal rate. These are soft items. You can read this. Right here, like I said, is APY EAR is used to compare returns on investments with different payments per year, also called APY, annual percentage yield. You can go to Capital One website and you can actually see that. And this is the final slide that I'll cover in this one. These are actually real life apps. These are examples that I've created. I mean, in fact, at a grad level, this is the only slide I should have done, assuming everything else, but I don't assume. And if you do these two problems, not only it indicates that you're fluent with time value of money concepts, but also you actually see how it actually works, and maybe to your disadvantage in real life, especially if you're on the receiving end. Let's see, for a $100,000 mortgage at 10% annual rate with 30 equal payments, what is the effective interest rate if there are 2 points? So first thing is this points things. So typically we like points, right? But with a mortgage, you don't want points. It's just a very basic way of saying that the sales commission is 2%. So if you have a mortgage with 2 points, so 2% of 100,000 is $2,000. Effectively, you're borrowing only $98,000 instead of $100,000. And typically, if your credit history is not good, if you have a smaller down payment, and if there are some other restrictive clauses, then your points are higher. Um, you can actually negotiate with the bank to have 0 points. If they have 0 points, then they can actually raise the interest rate, and so it's a negotiation. Or if you have a very good credit history, then you can actually have 0 points and a lower interest rate. That gets interesting. One thing which is not here, but it's just from experience, I want to mention to you is when you get your mortgage, just make sure it does not have something called a prepayment penalty. Prepayment penalty. Just see if I can type it here. Prepayment. You don't want a prepayment penalty. A prepayment penalty means, like, let's say you got a 10-year mortgage or a 30-year mortgage, and for some reason, a year, 2 years later, you want to pay off your mortgage. It actually happened to me. Like, I bought a house, and then I wanted to move to a different town, and so I had the house only for 11 months. And thankfully, I had a class in real estate finance in one of my masters, and I saw that buried in the hundreds of pages of document was prepayment penalty. And prepayment penalty would have cost me about $15,000. So I did not have the prepayment penalty, and so I could pay off the whole mortgage, and then just that. So these are some of the devil is in the detail, as you know. But anyway, first thing is, let's calculate the effective interest rate if there's a 2% origination fee. So straight through calculation of your mortgage payment is 10,608. I can show it to you, but it'll just take time here. 100,000 mortgage here. Let's see, $100,000 is your present value. Present value here. Number of years is 30. Future value is 0. Why is the future value 0? It's not there in the question here, because you pay off your loan, so you don't owe anything. And interest rate is 10%. And compute payment. See, right away, just like that, very quickly you could get the value of your mortgage. In this case, it's annual, but you can have monthly mortgage for 300. For 30, how would you make it a monthly mortgage? 30 times 12, make that 360. 360 would be n under n. And IY, which we had 10, do 10 divided by 12. And then you would get your monthly mortgage there. I'm not doing that because I want to just work through this. And, every minute is like 50 megabytes on this file. So anyway, so we enter that, and you get the mortgage amount, which is 10,608. However, see, now we are talking. Did you actually get $100,000? No, you actually got 98,000, because 2% were paid to the mortgage originator literally the first day of your mortgage. So let's take out 2,000 from 100,000, so that's 98,000. That's your present value. However, your payment stays the same, right? Payment remains the same. Your payment of 10,608 is actually calculated of the 100,000. So basically, its effect is to raise your effective yield, effective cost here. Compute IY. Oops, compute IY. Let's do this here. N is 30. Payment 10608. Future value 0. Present value 98,000. 10.24. So the effective yield is 10.24%. So while you thought that you had a mortgage at 10%, actually the effective cost of the mortgage is 10.24%, because your payment of 10,608 remains the same, whereas you actually borrowed only 98,000, not 100,000. Now enter present value of 2,000. and compute payment at IY of 10%, future value 0, you'll get a payment of $212. So what this $212 is showing you is that an extra $212 is built into this amount, a result of your initial points, which appears to be a small amount, right? So here's finally the final thing that we do. What's the future value of $212 at 10% over 30 years? That's 34,898. So let's just see that. $212 is your payment. You start off with nothing there, and 10% is the opportunity cost of money, also the terms of the mortgage, and N is 30. Compute future value. That's $34,000. So this is also, that's why I use this example apart from the TVM concepts, is something that appears to be so harmless, 2 points, is actually translating into a reasonably significant amount. This year, the second problem is actually my favorite one, and it's actually happening to almost everyone. This is basically what happens when you invest, let's say, in a mutual fund, which has a front end sales load, which is basically 3% commission, and a $1,500 flat annual fee. See, this $1,500 flat annual fee basically translates to 1.5%, which once again, people will think is a small amount, right? 1.5%. A lot of mutual funds, they basically have annual expenses from 1% to like 3% a year. And so I'm actually being conservative in this example. And they can even have like front end sales load of 4%. What does that mean? Let's see. Assuming a 10% annual return. So basically, the minute you went into that firm, you handed them your $100,000, they took 3% as sales commission just for investing in their fund, right? So your present value, so you gave them $3,000. No wonder they like you right there. It's $3,000, excuse me, is your present value. The payment is 1,500. So you've created a cash machine for the mutual fund. And we're once again being conservative at 1.5%. And I'm saying flat because, if your mutual fund goes up, if its value is $120,000 at 1.5%, that's what, $180. So, or $1,800. So in this case, $1,500 is basically you're creating a nice cash flow for them, annual basis, $1,500 payment. Recreate this example at your own end, and you'll see this is amazing. For 10 years, compute future value. Oh, must have done something. Compute. There must be some residual value from somewhere. Let's start again here on this one. $3,000 is what you left on the table. $1,500 is your annual expense. Interest per year is 10%. Number of years is also 10. Compute future value. There you go. $31,687. So the future value of the expenses that you have incurred in investing in let's say mutual fund is 31,000. But I want to be fair to the firm here, and this is, as we know, a dollar today is worth more than a dollar tomorrow. So what is the value of this $31,000 today? So this is how you do it. You have future value of this, enter payment 0, and compute present value. Yeah, this calculator has a memory thing here. So you have to, basically I'm noticing, see, this is an app that I had to buy to do this emulator mode, and I'm noticing that, but it's okay, it's fine. So we put future value of 31687, and payment 0, IY is 10, number of years is 10, and compute present value. See, 12,000. So this is a solid number, guys. Here, what this means is, here's the English translation of this. You went into a firm with $100,000 and you invested in their product, and you left $12,216 on the table. No wonder they're smiling when they see you walking there. And of course, when you walk out, you're gonna have a nice pen and an attaché case. But just remember uh, that at that very minute, you generated $12,216 in the present value of all the expenses that the firm will collect. And this is being very, very reasonable. That's why in your portfolio project, I've given, that you want to look at the expenses of what you're investing in, and you'll see there's like 12b1 marketing fee, redemption fee, even when you sell your fund, there's fee and all that. So everything looks nice and free and all that, but as you know, free is a four-letter word, FREE, and there is no free lunch. So anyway, that concludes this section of time value of money here, and this material is there actually on the next leg of the video. Thank you.